So in this problem, we have a circuit with series capacitors. So I have a voltage that's 12 volts, and it goes across two series capacitors, C1 and C2. And the question was, so C1 is is 2 microfarads, and C2 is 4 microfarads, right? Just for your recollection, is times 10 to the minus 6, right? And so the question is, what is the voltage across capacitor 2? Like that, right? And so this is V2, this is V1. So these guys each get a charge on them because of the voltage source. This guy gets Q2 and this guy gets Q1. And if we wanted to calculate this, we could go back to our definition of the capacitance, which is Q equals CV. And so then I get, I could say V equals Q over C, or for our case, V2 equals Q2 over C2. But we don't have Q2, so we can't calculate the voltage right away. And so what we have to do instead is figure out how we're going to do that. Now, one thing we can notice is that in a series circuit, Q1 equals Q2. That is to say, the charge that runs onto this guy is equal to the charge that runs onto this guy. This is the negative plate, and this is the positive plate. But they get the same charge because this is just a pump. It's not sending more to one side than the other. It's just moving charges to one side from the other. So, so those two charges are equal. It still doesn't tell us what they are, but that can help us recognize that, look, I can treat this combination of capacitors as a single capacitor, and I can call it C series. And it turns out that these guys will also be equal to Q series, because if I treat this as a single capacitor, the charge that runs onto this side of the capacitor is the same thing as Q1, and the charge that runs onto the other side of the capacitor is the same thing as Q2, since that's exactly what the two opposite plates in C series are. And so, so if I can calculate C series, then I know Q series, then I know Q1 and Q2. And so the first thing I have to do is calculate C series. And if you remember that series capacitors add in inverse, and so C series equal 1 over C1 plus 1 over C2, right? And so that's equal to 1 over 2 microfarads plus 1 over 4 microfarads, right? And so I can say 1 over C series is equal to, so 1 over 2 is the same thing as 2 over 4. So 2 over 4 plus 1 over 4 is 3 over 4 microfarads is in the denominator. And that's 4/3 microfarads, or if you want, 1.33, either one. Microfarads, sorry. That's what 1 over C series is. C series is the inverse of that, which is 4/3 microfarads, or 1.33 microfarads. Better. So now I can use this formula up here to calculate Q series. Q series is equal to C series times V, where this is the total voltage on the circuit, because that's what's across Q series. And so this is 1.33 microfarads times 12 volts, which is equal to 16. 1.33 times 12 is 16 micro. A farad is a coulomb squared per joule. You may have to look that up, and a volt is a joule per coulomb. And so this is 16 times 10 to the minus 6 coulombs. That's my Q series. And if you recall, we already said that's equal to Q1 and Q2. So now I know Q1 and Q2 are 1.6 times 10 to the minus 5th, or 16 times 10 to the minus 6th coulombs. And then I can say, look, V2 is equal to Q2 over C2. And so that's equal to 16 times 10 to the minus 6 coulombs over C2, which is 4 times 10 to the minus 6 farads, which is coulombs squared per joule. And so if you divide all that out, you get 4 joules per coulomb equals 4 volts. Now I know that, notice by the way, it's not 12 volts, right? When I'm looking at the voltage across this guy, it's 4 volts. I know that V1 has to be the rest of it. And so V1 is equal to 12 volts minus 4 volts is equal to 8 volts. If I'm not sure of that, I can calculate it the way I calculated V2. I can say V1 is equal to Q1 over C1. Q1 is the same thing as Q2 is. It's 16 times 10 to the minus 6 coulombs over 2 times 10 to the minus 6 coulombs squared per joule, because that's what 2 microfarads is, and that gives me 8 volts, just like I expected. And so from just the voltage and the 2 capacitances, I was able to calculate the series capacitance, the charge on either plate or on the combination of plates, and the voltage across each plate. So in this problem, I'm going to have 3 capacitors. It says 2 capacitors are connected in parallel, and so I'll have 2 capacitors in parallel. There'll be C1 and C2, right? This is equal to 0.5 microfarads, and this is equal to 1.5 microfarads. They're in series with the third. You see how that works? These 2 guys are in parallel, but they're in series with C3, which is 6 microfarads. So I'm going to start by just asking a few questions. Before we put a battery on there or anything, I'm going to say, what's the parallel capacitance of C1 and C2? So I'd say C parallel is equal to C1 plus C2. When capacitors are in parallel, you just add them, and that's equal to 0.5 microfarads plus 1.5 microfarads, and that's equal to 2 microfarads, right? So now I can ask the question, well, what's the total capacitance of the 3? Well, I just evaluated the parallel capacitance of these 2 guys. For these guys, Cp is equal to 2 microfarads, right? Now, Cp is in is in series with C3. And so I can say, look, 1 over C series, and now C series is the total capacitance of the full circuit. So C series is all of this, right? Is equal to 1 over C parallel plus 1 over C3, and that's equal to 1 over 2 microfarads plus 1 over 6 microfarads. And that's equal to 1 over C series is equal to 3 over 6 microfarads plus 1 over 6 microfarads, which is equal to 4 over 6 microfarads. And that means C series is equal to 6 over 4 microfarads, which is 1.5 microfarads. And so this is the total capacitance of the full set of capacitors. Okay, and so now we're going to continue this problem. So now we've just determined the series capacitance, and C parallel, I'll write it up here, is 2 microfarads, right? And then I'm going to erase part of this, and I'm going to say, given that part, so if there's 10 volts across the whole circuit, so now I can say, all right, look, so here's my circuit, and I put a battery across it here, and this is V equals 10 volts. And I'm asking, okay, when this thing charges up, what's the total charge on all these guys, on each of these guys, and what's the voltage across each one? And so we know that, the voltage across each of these is not 10 volts because it's 10 volts here, and so each of these is less. Just like in the last example where I had 12 volts across the circuit, and one was 8 and one was 4 volts, right? And they had different charges on them. So what we usually do in this case is we say, well, look, if I treat this as a whole capacitor, right, then a certain amount of charge runs up here. It gets to split between these two, but a certain amount of charge runs down here, and it all goes into Q3. And so if I determine my total capacitance is C series, right, so the charge that runs onto Q series is the same as the charge that runs onto 3, because this side of Q series is just C3. And so the charge that runs onto this part of the plate, when I treat all this as one thing, is just however much charge runs onto that plate. And so I can evaluate this thing. I know that Q series is equal to C series times V, and that's equal to, we already calculated that in the last part, 1.5 microfarads times 10 volts. And so that's 15 microcoulombs. If you remember that your farads is coulomb squared per joule and your volts is joules per coulomb, they cancel. If you want, you can write this as 15 times 10 to the minus 6th coulombs if you want. I'm okay, however you want to write that. You can write it either way. But now that's the same thing as Q3. Because again, if I treat this as all one object, the charge that runs down here for Q series is exactly the charge that runs onto C3, and so that determines the charge Q3 also. And so now I can calculate V3. V3 is equal to Q3 over C3, and that's equal to 15 times 10 to the minus 6 coulombs over the capacitance of this, which is 6 times 10 to the minus 6 farads, and that's equal to 2.5 volts. So right away that tells me that the parallel, the voltage across this parallel circuit is 10 minus 2.5 or 7.5. I can say V1 equals V2 equals 7.5 volts, or I should say 10 volts, the whole circuit voltage, minus what's across C3. Right? And that means that I now know the voltage across this guy and the voltage across that guy. And then I can say, well, look, Q2 equals C2 V2. And so that's equal to C2 is 1.5 microfarads times 7.5 volts. And so I better be a little careful how I multiply that. I think it's 11.25. Let me just. Yeah, it's 11.25. And this would be in microcoulombs. Right. And now I kind of know, this is, if I want to, I can say this is 11.25 times 10 to the minus 6 coulombs. Now I know that the total charge on these two has to be the total charge on that, because whatever it puts up here in positive, it puts down here in negative, so the total charges have to add up. And so if this is 15 times 10 to the minus 6 coulombs, and this is 11, 15 minus 11, the amount of charge on C1 has to be the difference between those two, which is 3.75. But we're just going to calculate it times 10 to the minus 6 coulombs. So we're going to say Q1 equals C1 V1, which is 0.5 microfarads times 7.5 volts, which is 3.75 microcoulombs. Just what we said is 3.75 times 10 to the minus 6 coulombs. And so now I have Q1, Q2, Q3, and then V1 and V2 and V3. So that's all of them for that one. We calculated the capacitance of the parallel part. We calculated the total series capacitance, and so forth. So when a capacitor is charged up, it stores energy in here, potential energy, and the formula for the energy is U is equal to 1/2 CV squared, as you saw in the video, where that's the capacitance and that's the square of the voltage. And so in this problem, we're saying right? And so we can just apply it directly. It's 1/2 times 5 microfarads times 12 volts squared, and this is 1/2 times 5 times 10 to the minus 6. So a farad is a coulomb squared per joule. 12 squared is 144. A volt is a joule per coulomb, but I'm squaring them. I squared the 12. I have to square the volts, which is a volt is a joule per coulomb, so it's a coulomb squared over a joule squared over a coulomb squared. The coulomb squared cancels, and one of the joules cancels, and my thing, which is an energy, comes out in joules, and that makes me happy. Let's set the 10 to the minus 6 aside for a minute. 144 divided by 2 is 72. 72 times 5, so 70 times 5 is 350. 2 times 5 is 10, so it's 360 times 10 to the minus 6 joules. If you wanted to, you could say that's 360 microjoules if you want, or you could say it's 3.6 times 10 to the minus 4 joules, depending on what units you wanted. Right? And so this tells you how much energy is stored in that capacitor after you've charged it up. This is a useful way to give out energy because capacitors can dump energy faster than batteries can. So you can take a while to charge it up, and then you can just dump the energy really fast. So like flash attachments on cameras and stuff like that often use capacitors to to run their lights because they wanted the light to just happen really fast. So we could do this problem a little differently. We can like reverse it and say well, we can look at this formula. We can say, look, U is equal to 1/2 CV squared, right? And if you remember, Q equals CV, and so V equals Q over C. And so I can say this is 1/2 C times Q over C squared, which is equal to Q squared over 2C. And so you can write the energy in terms of the charge and the capacitance. And so we can say what's the charge on the capacitor, right? And so Q is equal to 2C times U from this equation. Sorry, Q squared. And I can say Q, keep the same Q, is equal to the square root of 2 times the capacitance times the energy stored. And so Q is equal to, so it's the square root of 2 times 5 microfarads times 1.6 microjoules, right? Which is equal to, so a farad is a coulomb squared per joule, divided by times a joule gives you just a coulomb squared. The square root of that gives you a C. If I have a 10 to the minus 6 times 10 to the minus 6 and square root it, I just get a 10 to the minus 6. And then 2 times 5 times is 10. And so times 1.6 is 16. The square root of that is 4. And so I did each one of these and took the square root. Micro times micro gives me a micro. Micro times micro square root, it gives me a micro. Farads times joules, square root, it gives me a coulomb. And 2 times 5 times 1.6, 16 square root gives me 4. And so the charge on my capacitor is 4 microcoulombs. I could also calculate the V, right? The V equals Q over C, which is 4 microcoulombs divided by 5 microfarads, which is 0.8 volts maybe. This is from the previous problem. I was just keeping the diagram there. All right. That's it.